Hi, everybody. I hope you're doing well. Today, I want to talk to you about the consequences of specific heat and about heat transfer. Um, we had already talked about what specific heat is, and we've done a specific heat lab, but some of the implications of specific heat are around us every day. A good example of this is going to be if you are baking and you put something onto a piece of aluminum foil, what you'll find is that when you take out the metal tray and you place it on the counter or on the hot plate or on the device to hold it, that like the stove that won't melt, you can touch the aluminum foil pretty quickly. And the reason that is because aluminum has a low specific heat, and so it cools down much quicker than the food that was being cooked, or maybe even the steel tray that it was being cooked on. The other areas where you might see specific heat in your daily life is with a pool or with water. And right here in front of us, we can see a diagram of a beach. What happens here? This is a really interesting phenomenon, and when you have an opportunity to go near water, take note of this, especially large bodies like the beach. But what happens here is that during the day, the water temperature is going to be heating up. And that means that in early spring and early summer, even, the water temperature is going to be lower than the air temperature around it. The amount of energy to raise the air temperature is much, much, much lower than the amount of energy required to raise water. It takes 4,180 joules of energy to raise 1 kilogram of water 1 degree Celsius. Just imagine all the water in the ocean and how much energy we have to put into that to heat up the water. So it takes a long time to heat up. And so all summer long, there is a greater amount of sunlight than darkness. The temperatures are higher than the water temperature for a large majority of the day. And so what that means is that all summer long, the water is heating up. If you go to the beach in late August, that is where, in early September, that is when the water temperature has reached its maximum value. After that point, it starts to cool off again. So there's a lag in water temperature reaching its peak. So the peak sunlight is June 21st, but we may not see the peak water temperature until August 21st, because all summer long, the water temperature keeps rising and rising and rising. Because water has a high specific heat, it holds that heat for a very long time. And so at night, the air temperature drops very quickly. The air has low specific heat, so the air temperature drops very quickly. And the water temperature, although it may drop slightly, it won't drop as much as the air temperature. And so if you go in the water in early June at any point, and the water feels cold, it's probably because there is a higher temperature in the outside air than in the water. If you go in that same water at night, it may feel warm because now the air temperature is lower than the temperature of water. So there's this lagging motion of the temperatures rising and falling of water, where the water temperature lags the sunlight. So the coldest ocean temperatures are not on December 21st, but probably January or February 21st. If we follow our weather patterns, we can see that this makes some sense, because even though there's more sunlight on June 21st and July 21st, our highest air temperatures are around July 21st. And that's because we have not just the water taking time to heat up, but the trees and the grass and the concrete and everything on Earth just keeps increasing in its temperature. Right after July, the end of July, things start moving back down towards a cooler temperature, because the days are becoming shorter, the amount of energy is becoming less, and so you reach a peak air temperature Around August 1st, you reach a peak water temperature around August 15th, 21st, somewhere in there. And so that's why you see a lot of people trying to get to the beach in the late summer, because that's where the greatest water temperatures are going to be. Now, some of the other consequences to this are wind. And so we know that hot air rises and we know that cold air settles. And so what you're seeing here in this picture on the screen is a beach, and the air over the beach is going to rise because the beach is going to be very hot. And then as it rises, additional air has to slip in because we can't have a vacuum. So it's pulled in off of the water in the surrounding area, creating a convection current. The hot air, as it goes over this cold mass of water, the water will be cooler than the air during the day. It sets, and we therefore get a convection current. And so during the day, if you watch kites, they will move generally. Now, there are other wind patterns occurring, but if it's a calm day, you can always get a kite flying at the beach because the hot air is going to rise over the beach and it is going to move outward. So the kite is going to be flying outward. Now, move ahead 12 hours until night. And at night, as I mentioned, you are going to see the water temperature being hotter. And so you are going to see the air rising over the water, and the beach is going to be cool. If you walk on the beach at night, you'll feel that cold air, the coldness in your feet. And so the air is going to be settling. And so you get a pattern that goes in the opposite direction at night. And so at night, if you watch kites at a beach, they generally are moving inward. And that is because there is a difference in the air temperature to the ratio of air temperature to ground temperature or water temperature during the day and night. It's a really interesting phenomenon. These are some of the consequences of specific heat, and the fact that the water takes longer to cool down because it has a higher specific heat than the air and the sand. We talked about calorimetry. What I want to talk to you now is about phase change. Phase change occurs when substance changes from a solid to a liquid to a gas. Those are phase changes. So solids to liquids are melting, liquids to gases are boiling. These are two important points. I know you know these. We're going to talk about all of these values on a later slide, but phase change is occurring when this happens. There are, at the melting point and the boiling point, special energies that are required to break apart the bonds. So if you have a solid and you want to turn it into a liquid, it's not just a matter of heating it up, but it's heating it up and breaking the bonds that are holding the molecules together. And so these extra energies needed to break the bonds are called latent heats. And you will see that latent heat has its own equation. Changing the temperature of a substance was Q is equal to mc delta T. Then that would be the change in energy over a range of temperatures. But this here represents the latent heat. It must be added into our equation. L being the specific heat, the latent heat constant is a specific value by material, just like the friction has the coefficient of friction, just like the expansion coefficients are specific. In this particular case, there's a specific chart that you would go to find out what the latent heat constants are for different materials. Latent heat is measured in joules per kilogram, which makes sense because it's ultimately going to lead to energy. So if we look at the equation, we're taking joules per kilograms times kilograms, and that means we will just get joules, which is the unit of energy. Here is a graph of ice to steam, and I want to go through what is happening here. The next few slides in your notes will actually say what I'm about to say. I'm not going to go to them. I'm just going to look at this picture here. So we start off with water at -30. It is super cooled ice. And then it takes some time for that ice to rise up in temperature. So there would be, for that range, Q is equal to mc delta T. Now, the specific heat of ice is different than the specific heat of water, so you need to take that into account when you do your calculation. So you apply energy. What's happening here? There's a couple ways this graph can go. This is the temperature up the y-axis. This is energy added. We could also do time. So when we use the hot plates, for example, we know that the energy added is at a constant rate, and so we can look at it in terms of time. Maybe we don't care that about the exact amount of energy, but we care just that there's constant energy flow in, so we can get a nice graph like it's on your screen. So sometimes it's time down here. In this case, it's energy in, and our assumption is that energy is being put in at a constant rate, 5 grams per second or 500 grams per second or 5,000 grams per second, whatever it happens to be. And that will give you this nice curve we have. If we change the rate at which it goes in, the curve will not look so smooth because you're not constantly putting that energy in. So we are looking here again, it's going to take some energy to rise it to this point. We reach the 0 degree level, and at that point, we are at the ice and water level. The water temperature is, the ice starts to melt, and it's the ice and water will stay at the same temperature until all the ice is melted. We cannot get a rise in temperature until all the ice is melted. And so what happens is the energy is put in to break apart the ice bonds. And so in that case, we get a Q is equal to ml. We then, once all of the ice is melted, we then are going to see a temperature increase again. Q is equal to mc delta T. And then we get to steam, and we have another latent heat that is going to occur. So that's Q is equal to ml. And then there is finally another specific heat, Q is equal to mc delta T. So these 5 values, whatever these 5 Q's are, could get added together. And when they do, it ends up to be about 3,110 joules of energy that get added together. So each one of these segments, 1, 2, 3, 4, and 5, all get additional energy added to them as we move along here. And so Q equals mc delta T is a very important part of this, but a lot of students miss the heat required to break apart the bonds. And so in the lab experience that you had with me, you saw it took time to break the ice bonds. Make sure you recognize that its energy is still going in from the hot plate, and what that energy is doing is it's breaking the bonds. And so that's what's explained in the next few slides. You can go through this and get the exact values and the exact specific heats if you would like, but know how to calculate this. Phase diagrams help us understand how materials go through various phases. So we go from solids to liquids to gases. At normal, and I'll be honest, and this is studied a lot more in your chemistry classes, but at a normal temperature, normal pressure of which runs across here, we can see, and this is carbon dioxide, that carbon dioxide goes from a solid to a vapor. It doesn't go into liquid form, and it changes from a solid to a vapor at about negative 80 Celsius. If I want to get it into liquid form, I need to apply pressure. And when I apply pressure to it, so let's say I'm at 0 degrees Celsius and I apply pressure, I can get it to go to a liquid, I can get it to go to a solid. So what makes something a solid or a liquid is how closely those bonds are together, and by applying pressure, I can force them together, or I could change the temperature, which changes how fast they're moving. And so, as you can see here, there are 2 ways to get from a vapor to a solid. One is to add more pressure, and the other is to adjust the temperature, to drop the temperature. The graph on the right represents water, and so we know that water changes from an ice to water at 0 degrees Celsius, and we know that it changes from water to gas at 100 degrees Celsius, and this is all happening at 1 atmosphere. That makes sense to us. But what you might not realize is that if I drop the pressure, I can make the water vaporize. By dropping the pressure down to a lower rate, in this case, we can see that we can get to water vapor and turn the water from a liquid into a gas. Just like we did on the right side, we turned into a liquid to a gas by dropping the pressure. And so we're able to do that here. But we're also able to take that water vapor and lower the temperature and get a value where it turns to ice. So you, depending on which way you're moving on this chart, you can get a solid, a liquid, or a gas. And it's dependent not just on temperature, but also on pressure. I think that's an important part of this. The process of sublimation and deposition are going to be talked about in terms of what happens when we go directly from a gas to a solid. So this chart here is important to know these terms. We're familiar with them, but let's just make sure we review. So when we go from a solid to a liquid, we melt. When we go from a liquid back to a solid, we freeze. When we go from a liquid to a gas, we vaporize. When we go from a gas back to a liquid, we condense. But then there are these values or these concepts down here about sublimation and deposition, which describe what happens when we go right from a solid to a gas or a gas to a solid. Just knowing where they fall is an important part of this, so please be aware of that. The next time we talk, we are going to talk about energy transfer. If you have any questions, please let me know.